Hey 7th graders, so hopefully you guys just completed the populations review and are seeing this video. If you guys haven't finished something, obviously do your best to try to finish first. Be honest, I can't check you guys on this, so make sure if you guys aren't done and you're seeing this video first for whatever reason that you guys go back and do it right, so you guys are actually a little bit more prepared for your test. But I'm just going to go through some of the answers on this key. You guys will kind of be able to check, and I'm going to do a lot of explanation, so you guys kind of know why I'm answering the way I do, especially if you got it wrong. Okay, so moving on to the first slide, what are two general reasons a population could decrease its size? So the first one is more deaths than births, so we have more individuals dying than are being born. And then also migration, so specifically emigration when they're moving out of the population. Really when we talk about like more predators or less food, those kinds of things, those kinds of examples are all going to lead to either death or animals moving away. Okay, if there's less food, they're either going to die of hunger or they're going to move away. If there's a lot of predators, they're either going to die from predation or they're going to move away. So those really are the two main causes for a population to decrease. On the other hand, you guys have increasing, same kind of thing, more births and deaths and migration. Everything's looking good in that environment, so animals are moving in. Okay, so those two things are the reason why you might see a population increase. If a species has more births than deaths, what will happen to the size of that population? It's going to increase. If you have more deaths than births, your population will decrease. Next slide. If a species has about equal births and deaths, then that population will be stable and stay the same. What kinds of activities would an organism use an energy storage molecule for? So, the biggest thing that we talked about in the Amplify units was reproduction. In order to reproduce, you've got to have an ample supply of energy storage molecules. Literally, you are growing another being, okay, whether it's a bacteria or another human, whatever, that takes a lot of energy. Other things you guys might see is obviously being able to hunt or forage for food, evading being someone's food source, competition, whether that's like competition for territory or breeding or just area or water, whatever the case. Competition's a huge energy suck. And then migrating, whatever else you guys can think of. There's a lot of options there. What is a consumer population? It's a population that needs to eat for energy, so it's something that can't make its own food. So really anything outside of plants that are autotrophs and can make their own food with photosynthesis, those are all consumer populations. Okay, resource population is something that gets eaten, so it might be something that's also a consumer, or it might be a plant. So you can look at like things like plants obviously get eaten a lot for energy, but a deer gets eaten too. So that's also a resource population. Okay, we have this little food web here. This should look a little bit familiar to you guys. What is considered the consumer population? That's the lynx, because it does the eating. And what is considered the resource? The roe deer, because it gets eaten. Those are the only two organisms in this food web, so those are the only options you guys have for answers. What does the roe deer provide to the lynx? That little arrow represents energy. So the roe deer is giving its energy to the lynx when the lynx eats it. Okay, if the roe deer population increased, what would happen to the lynx population? That one, so if you have an increase in our roe deer, the lynx population would have more to eat, so it would increase. Okay, all right, moving on, next slide. Same little food web here. If the lynx population increases, so we have more lynx, what would happen to the roe deer population? Well, if we have more predators, we're going to have less prey because they're eating more. And the more they eat, the harder it's going to be for the roe deer to reproduce if they're always worried about being preyed upon. So more predators means less prey, so they decrease. Would this change be direct or indirect? This is going to be direct because there's only one arrow connecting them. They get their energy directly from each other. And then what type of community interaction is described by the lynx and the roe deer? So we're talking predator-prey there. So we can talk about that whole circulation. If our roe deer decrease, our lynx are going to have less to eat and they're going to decrease. If our lynx decrease, the roe deer are going to have a chance to reproduce and increase. And then if our roe deer increase, then we're going to have more food available for the lynx, so they're going to reproduce and increase. And that's just going to keep cycling through that increasing, decreasing wave of populations between the predator and a prey. Just something we typically see in predator-prey relationships. Okay? All right, moving on. Use the food web to answer the following questions. In the food web, What 2 organisms can be considered resource-only population? The only 2 that we have here that are strictly giving their energy to another organism and not getting their energy from anywhere are phytoplankton and our seaweed. Okay, in the food web, what 2 organisms can be considered consumer only? Those are the ones that are only doing the eating and not getting preyed upon. So those are going to be our blue whale and our killer whale. Okay, next slide also uses this exact same food web. What are 3 examples of competition in the food web? I'm just going to go back and answer on this slide. There's definitely more than 3 here. So if we look, the fish is one of them. Looks like the seagull and the leopard seal are competing to eat the fish. So our competing organisms are actually our seagull and our leopard seal. Looks like leopard seal and a killer whale also compete for penguins. Looks like a penguin and an elephant seal compete for squid. The fish and the blue whale compete for krill. And there might be another one. Maybe the zooplankton and the krill compete for phytoplankton. There might be more. I'm just kind of trying to brush through the ones I can see quickly. So if you guys see more and you're unsure, let me know. But I think that might be it. Okay? All right, moving on so that you guys can see the 3 that I used. But again, that doesn't mean there's not just 3. All right, so now we're back to this one. You guys are going to see this food web a lot, especially on the test. In this food web, what 2 organisms are in competition? Same as what we just did. We have the moon jelly and the walleye pollock are competing for the zooplankton, so they both eat the same resource. Okay, oops, I thought that was racer. All right, and then what resource are they competing for? The zooplankton. All right, same little food web there. If the population of the moon jellies decrease, so you guys can go ahead, hopefully mark this up if that helps you, if you didn't already do that in the instructions. But if the population of moon jellies decreases, what would happen to the number of sea turtles? Well, if there's less to eat there, they're also going to decrease. So decrease, and that's going to be a direct effect. Okay. Next question. If the population of sea urchins decreases, they're the predator in this small little food web here. So if the population of sea urchins decrease, what would happen to the number of kelp? Well, they would be able to grow because they'd be eaten less. Okay, so that would be an increase, and that's also a direct effect because there's only one arrow connecting those 2 organisms. Oops. All right. Moving on to the next slide. These all involve the same population, and there's a lot of explanations that we're going to talk about on these. If you wanted to decrease the number of moon jellies, so our moon jellies would need to go down, how would you change the walleye pollock population? We would want to increase those. So if we increase the number of walleye, that's going to mean that we're eating more zooplankton, so our zooplankton is going to go down. And if our zooplankton goes down, then our moon jellies have less to eat. They're not going to be able to reproduce. We're going to have maybe less births, more deaths. That's going to decrease our moon jelly population. Okay, and again, that is going to be an indirect effect because they're not directly connected. There's no arrow connecting the moon jellies to the wall-eyed pollock or anything. Okay? All right, moving on. If then the population of walleye pollock decrease, what would potentially happen to the number of sea turtles? So if we decrease our walleye pollock, that means our zooplankton would have a chance to reproduce and grow. There'd be less deaths than births, basically. So our births would cause our zooplankton to grow, which would cause our moon jellies to grow because they have more to eat, which you need ESMs for reproduction, so they would grow, more births and deaths. And that would cause an increase in our sea turtles as well because, again, they have more food to eat and are able to reproduce more. And again, that is an indirect effect. If you wanted to increase the orca population, what change might you make to the zooplankton? Okay, so let's kind of work backwards for this. So if you guys look at this, okay, if we want to increase, that means we need to have more sea turtles. And in order to increase our sea turtles, we need to have more moon jellies for them to eat. And in order to increase our moon jellies, we would need to increase our zooplankton as well. And so I kind of explained that in reverse is, you know, if we're looking at a direct line in this food web, the more food an organism has, the more reproduction it can go through, therefore more births over deaths, and that should increase our whole line there. And that, again, will be an indirect effect. Okay. All right, next one. I think this is the last one with our little food web here, and then we're going to speed through the other ones. If you wanted to increase the algae, so this one's a little bit different. This one's a little bit harder to think about. If you wanted to increase the algae population, what should you make? What change should you make to the walleye pollock? Okay, so let's again kind of work backwards. If we want to increase our algae, we need to have less organisms eating the algae, allowing less death, more birth. Okay, so we would need to decrease our zooplankton. Okay, in order to decrease our zooplankton, though, we're going to have to increase our walleye. So the walleye pollock, if they increase, will eat more zooplankton, and the zooplankton population will decrease. Then if there's less zooplankton eating the algae, that allows the algae to have less deaths and births, and that will cause our algae to increase. And again, this is indirect. Okay, so they're kind of fun to think about. I don't know if you guys enjoy thinking about those and doing a little investigative work, but I enjoy those. What are 3 types of community interactions? This is straight out of your guys' notes that you should have done. Competition, predator-prey, and symbiosis. And define competition, competing for resources such as food, mating, territory, etc. What is an example of competition? I mean, you really could put just about anything on this one, but maybe 2 carnivores like wolves and bears competing for elk, or multiple elk competing for mates in a herd. So, I mean, you guys could add a lot of options. Those by far are not the only options you might have. What are 3 types of symbiosis? So mutualism, commensalism, and parasitism. Obviously, they're right here, so hopefully you guys got that one pretty easy. Again, this should all be in your notes. Mutualism, if you guys see the word mutual in there, that's where both species are benefiting. So that the example I gave you guys in the notes was a honeybee and a flower. The honeybee gets to pollinate for the flower, but in return, the honeybee also gets the pollen to take it back to the hive and make for food. Commensalism is a relationship where one species benefits and the other is neither helped or harmed. So it's not affected at all. It's not annoyed by the other species, nothing like that. The example I gave you guys on that one was like barnacles and a whale. The barnacles don't hurt the whale, they don't help the whale, but the whale moves the barnacles around, allowing them to get food, which is very helpful for the barnacles. All right, explain parasitism, a relationship where one species benefits and the other is harmed. So on this one, again, one species benefits, the other is harmed. This would be like a tick in a human or a tick in a dog. They're sucking blood out of it, potentially passing diseases. The whole point of the parasite is to not kill its host, because then it has to find a new host, and that's a pain in the butt. So really, they want to keep it alive. But with that being said, it still harms them. Okay, you guys should have completed your wrap-up. 4, 3, 2, 1, how do you guys think you're going to do? Hopefully from watching this video, you guys are now in this area. Okay, and then don't forget to hand it in. I hope you guys have a great day. I'll talk to you soon.